All right, so in today's video, we're going to be going over 3 problems from Griffiths. We're going to be doing the electric field of a finite line charge, a ring, and a charged disk. So let's start with example 2.2. I'm going to be solving this problem a little bit differently than they do in the example. So we want to find the electric field, a distance z above the midpoint of a straight line segment of length 2L that carries a uniform line charge lambda. So let's first just draw our own picture. So we have a line charge that goes from negative L to L. We're measuring it at some arbitrary point z on the z-axis, and it's a line charge of lambda. Okay, so the first thing we want to do is obviously just write down our formula for finding the electric field. So we're going to be using the integral. And so we're going to be using the full integral over the charge distribution form to find the electric field. In my next video, I'll do these exact same problems, but using the potential, and you'll see that using the potential is a lot easier than doing it this way. Okay, so a couple things about this integral. So the most important thing to remember is that you're integrating only over your charge distribution. So the primes here, the r prime and the tau prime, just mean that you're not integrating like over all space, you're just integrating over your charge distribution. So these r primes, the primes just refer to wherever there is charge, so your source points. So in this case, our d tau, tau usually refers to a volume integral. We're not actually going to be doing a 3D integral in this one since our charge distribution is only one-dimensional. We're just going to be doing a 1D integral. And then these fancy r's just represent the distance from your source point to your field point. So the source point is a point of, that's the source for the electric field. So our source points are all the points from here, from negative L to positive L, where there's charge. So this is a source point, this is a source point, all of these are source points. And so the distance, fancy r, would just be this distance here, which goes from your source point to your field point where you're measuring the field, which in this case is just some arbitrary point z along the z-axis. And this will be the case for every single point in our charge distribution. So we have a little curly r distance for each single point in our charge distribution. So we're going to talk about that more in a second. All right, so let's try to figure out some of these things in our integral here. So our rho, so this is just our charge distribution. In this case, our charge distribution is simply lambda. We just have a line charge and that's it. Now our d tau, our line charge is only on the x-axis and it's only in one dimension. So our d tau prime is just dx, because we're only going to be integrating along the x direction. And we're going to be integrating from negative L to L. And then let's find fancy r. So our fancy r is the distance from our source point to our field point. And it's important to remember on extended charge distributions like this r is going to change for every point in our charge distribution. So let's find r for just, let's say the end point here. Well, this one's pretty easy. It's just Pythagorean theorem, because we know that this side here is length L, this side is length Z, so R is just going to be L squared plus Z squared, and that's it. But what if it wasn't the end point? What if it was some arbitrary point in the middle? So what if instead we were looking at like a point here? Well, this one we can also use the Pythagorean theorem. So in this case, this length here would just be whatever this x position is, whatever this x coordinate is. The length of this side is just x. The length of this side is still just z. So again, we just have the Pythagorean theorem, but it's x squared plus z squared square root, and that's it. So you can see that we can actually do this for every single point along our charge distribution. It's going to be the exact same thing on this side because it doesn't matter that will be negative since it's getting squared anyway. So this is our distance for every single point along our charge distribution. So our squiggly fancy r is x squared plus z squared, where x is variable. All right, so now let's write our integral with what we have so far. So we have 1 over 4 pi epsilon naught. We're integrating from negative L to L. We have our rho is just lambda. R, fancy R squared is going to be x squared plus z squared. And now you might be tempted to say, okay, well, then my d tau is just dx and I can integrate. But that's not 100% the case because we have to take into account this r hat vector. So this r hat vector is just a unit vector in the direction from our source point to our field point. So if we look at that endpoint again right here, our r hat vector will just be pointing from the place with charge to the place where we're measuring our field. So in this case, since we have a positive charge distribution, our r hat vector is the same as the direction of the electric field from that point. So let's zoom in here a little bit. So I can just replace this. This is the same as my electric field vector. So my electric field is pointing sort of at a diagonal like this. And I'm just going to extend this a little bit so that you can see it's coming like that at the point where we're measuring our electric field. Okay, so this is the direction of my electric field at this point due to this point. Now I can see it's kind of at an angle there. So if we were to just go ahead and do this integral, it would not be correct because we're not taking into account the fact that the electric field is actually at a little bit of an angle. It's not perfectly along the z-axis or perfectly along the x-axis. So we'd be sort of ignoring the fact that it has components. And now I can make this a lot simpler for myself by noticing that there's a very high degree of symmetry here, and some of my components actually cancel out. So I have an electric field coming this way from this point, but I also have the exact same magnitude electric field coming from the opposite point, right? So there's going to be the exact same magnitude electric field coming from that opposite point on the other end of the finite line. And you can see now that some of the components are going to cancel. So if I break each of these up into its horizontal and vertical components, I can see the horizontal components are going to cancel, right? Because the horizontal component of this one is in this direction. The horizontal component of this one is in this direction. And the vertical components are in the same direction. So I can see that the horizontal components are going to cancel and the vertical components are going to add. So this component will cancel out. And this component will cancel out. And then all I'll be left with is this vertical component that I have to worry about. And you can see that this is going to happen for every single point along my line charge, whether I look at this point or this point or this point or this point or this point, there's going to be a corresponding point on the other side that's going to exactly cancel the horizontal component, and the vertical components will not cancel and they'll add. So I only need to figure out the z component of my electric field because I already know now that there's going to be no x component. There definitely won't be any y component. So all I have to worry about is my electric field in the z direction. But how do I figure out what is the vertical component of every single piece of electric field here? So I can just take this angle here, and then the vertical component will just be the cosine of my vector. So I'll just have like e cosine theta, and that will be my vertical component. So, okay, so let's just write that in. So let's just put in a cosine theta here for now. And this is in the, we're integrating dx in the z hat direction. Okay, so now obviously we have to figure out what cosine theta is because we need it in terms of x's and z's and stuff that we can integrate over. So it might seem like we don't know what cosine theta is, but we actually do. So if you think back to like your geometry class, this angle here and this angle are the same. So this is also theta, and I can definitely figure out what cosine of this angle is. Remember, cosine is adjacent over hypotenuse. And the adjacent side here is just z. So this is just some height z from here to here. So my adjacent is just z. And then my hypotenuse, I already know because we already figured out what the distance from our source point to our field point was. And we said it was x squared plus z squared, square root. So that's my cosine theta. So I can just now take this, put that into my integral, and now I have a kind of ugly integral. But let's write this all out. So we have e is 1 over 4 pi epsilon naught. We're integrating from negative L to L. We have lambda over x squared plus z squared. And then our cosine theta is z over x squared plus z squared, square root. And then we have dx, and our vector is in the z hat direction. Okay, so now let's condense this a little bit. So I can obviously write this all as one fraction. I have x squared plus z squared to the power of 1, x squared plus z squared to the power of 1/2. So I can just rewrite that as lambda times z over x squared plus z squared to the 3/2. And again, we were able to get here because we said that cosine theta was equal to z over square root of x squared plus z squared. Okay, so now we can solve this integral. So this is actually a pretty ugly integral to solve because you are not integrating over z. So z here is treated just as a constant, but we are integrating over x. So this is the kind of integral that I would not expect my students to do by hand. I would just give you a table of integrals. You could look up your integral and just write down the answer. Some professors might want you to actually do this integral. So I'm just going to write down the answer for this integral. If you want me to go over like actually solving it by hand, let me know and I can do that. But for now, we're just going to take this integral as a given. So let's just rewrite it so that all of the constants are outside. So this will be 1 over 4 pi epsilon naught. Our lambda and our z are both constants. And then we'll just be integrating from negative L to L. We'll just have dx over x squared plus z squared 3/2, and that's all in the z hat direction. And one more thing before we solve this integral, you really have to be careful with this r hat vector, because as we saw, the r hat vector, the direction of it depends on where you are in your integral, basically. So as you integrate along your charge distribution, the direction of this r hat vector will change. And that's the case for any vectors that are not just x hat, y hat, and z hat. So you should never integrate over like r hat or phi hat or theta hat, because they change direction as you integrate. So you always want to get your vectors into either x hat, y hat, or z hat, because those are fixed. They don't change direction as you integrate. So we have our integral, we have our z hat here. So we can just write down or look up the answer to this integral. So this comes out to x over z squared, square root of x squared plus z squared. And we evaluate it from L to negative L. Okay, so then this will all come out to, we have our lambda z over 4 pi epsilon naught out here. This will give us L over z squared L squared plus z squared, and then minus a negative L, so we'll have plus L z squared, L squared plus z squared. This is all in the z hat direction. And then we can see that these two terms just add up. So this part here will just add up to 2L over z squared, L squared plus z squared. So our whole integral will end up being, our whole electric field will be 1 over 4 pi epsilon naught. And then we'll have 2 lambda from here, 2L Our z cancels because we have a z over here and a z squared over here. So then we'll have over z, and then we have square root L squared plus z squared. And that is in the z hat direction. Okay, so that is our final answer for that one. I personally recommend always leaving your 4 pi epsilon naught, especially for kind of ugly integrals like this. I would always just leave your 1 over 4 pi epsilon naught just like separate. There's no need to cancel the 2's and stuff. It just makes things clearer, especially if you're going to be, if this is like on a test and you're going to be getting graded. It makes it a lot easier for the grader to kind of see where you went wrong. So I would always just recommend leaving your 1 over 4 pi epsilon naught sort of just by itself as its own constant, and then whatever else you have over here. So that is our electric field of a finite line charge. Now let's do the electric field of a ring. Okay, so this is problem 2.5. So this is find the electric field, again, a distance z above the center of a circular loop of radius r that carries a uniform line charge of lambda. All right, so first things first, let's write down our formula for finding the electric field. Okay, and then let's write down what we know. So rho we have is just lambda. This is just a line charge again. And now what is our d tau? So this one is a little bit tricky because we want to do it in cylindrical coordinates. So d tau, we're going to be integrating in a circle over cylindrical coordinates. So that would just be in the phi direction, but you have to be careful when you're integrating in cylindrical or spherical coordinates. You might want to say, okay, well, I'm just integrating with respect to d phi and that's it. But d phi actually comes with an r. So I'm not going to get into the details of how to integrate in spherical or cylindrical coordinates, but if you go to Griffiths on mine it's page 44, equation 1.77, where he goes over integrating in cylindrical coordinates, you can see that your line element in cylindrical coordinates in the phi direction carries an s or an r, whatever variable you want to use. So if you're integrating just with respect to d phi, you have to do r d phi or s d phi. So, okay, I use r instead of s, so I have to put in that extra r there. So that's actually my integration, not just d phi. So, okay, so now we have that. So, and I'm ignoring some of my primes. Now my fancy r. So fancy r is just the distance from your source point to your field point. So in this case, we're just going from some point on our wire loop to our point up here, P. So this is R. And I can see here that this is just going to be another right triangle. So I'm actually going to change this radius R. I'm going to make it a capital R just to differentiate it from the variable of integration, lowercase r. So now, this one's actually easier than our previous one because now my distance isn't changing, right? The curly r distance from every point around my wire loop is the same because the radius of the wire loop isn't changing. So everywhere around my wire just has the same distance. And now for my r hat, my fancy r hat vector, so we can see the same thing is going to happen as in our previous example. So the electric field, let's say from this point right here, is going to be going in this direction. And then it's going to have a corresponding point on the other side of the loop that's going in the opposite direction. And we're going to end up with the exact same thing where the horizontal components cancel and the vertical components add. And that's going to be true for every single point around our loop. If you do a point back here, the horizontal component is going to get canceled by a point over here. And so that's the case for every single point. So now we can just make our symmetry argument and say, okay, well, I know that my electric field, my final electric field is just going to be in the z direction. I'm just going to take the cosine of my integral, and that's it. So let's write all that down. So now we have 1 over 4 pi epsilon naught. We're going to be integrating from 0 to 2 pi because we said we're just integrating around the circle. Our rho is lambda r squared, fancy r squared, is just this. And then we're integrating, we're going to have a cosine theta again, and then we have an r d phi. And so our cosine theta is exactly what we found in our previous problem. It's going to be z over r squared plus z squared. So it's just going to be adjacent over hypotenuse. Okay, so now let's just write this again. So we're going to have 1 over 4 pi epsilon naught. We're integrating from 0 to 2 pi. We have lambda r d phi. And then we're going to have an r squared plus z squared to the 3/2 again. And then we also have a z. So we have the r squared plus z squared to the 1, and then we have the 1/2 from the cosine here. So we end up again with 3/2. Okay, so now one other thing. This r is actually not a variable. It's a fixed radius, right? Because we're not actually integrating with respect to r at all. So this is actually just capital R. And now we can see that we actually don't really have anything to integrate here. So there's no phi in our integral, and we're integrating with respect to phi. So our whole integral can basically, or everything here, can just be pulled out of our integral, and all we're left with is just 0 to 2 pi d phi, which is just 2 pi. So now I can rewrite my answer. My integral's done. So I can rewrite everything as just 2 pi r z lambda over r squared plus z squared to the 3/2. And this is in the z hat direction again. So that's it for our charged loop. There's really nothing to integrate. Now let's go on to a charged disk. Okay, so this is pretty much the same as our previous problem now, except instead of a ring, we have a disk. So we have find the electric field, a distance z above the center of a flat circular disk of radius capital R that carries a uniform surface charge of sigma. So this now is solid, and it has a surface charge of sigma. All right, so first thing, write down our formula for the electric field. And then let's write down what we know. So let's write down our rho first. So rho in this case is just sigma. It's just our surface charge. And now our d tau. And now what are we going to be integrating over? Well, this is going to be a 2D integral because we have a surface, so that's 2D. And we're going to be using cylindrical coordinates again. So we're going to be integrating, when you integrate over a disk, that's going to be in the r direction and the phi direction. So we're going to be integrating dr and d phi, and that means that we have r dr d phi. Okay, and now our fancy r. So what is our fancy r? So if we pick a random point on our disk, it'll be some distance to our point, and we can kind of see it's just going to be r squared plus z squared, square root. So, right, whatever coordinate, whatever distance r this point is at, that will be this side here, the length of this side. And they're all the same distance z from the point where we're measuring our field. So this will be the distance for every single point, where this r now is a variable that we're going to have to integrate over. So this r changes depending on our source point. Okay, so that is our fancy r, is r squared plus z squared, and our r hat, you can kind of see the same exact thing is going to happen as our previous two problems. Our electric field is going to be only in the z direction, because our electric field from this point here will be canceled from a corresponding point on the other side, and that's going to happen for every single point. So we're going to have the exact same thing again, where we can just take the cosine and then say, okay, our electric field is in the z direction, making our argument from symmetry, and then we just have to do one integral. Okay, so let's write this all down. So we have the electric field is equal to 1 over 4 pi epsilon naught we have a 2D integral, so we're going to be integrating from 0 to capital R in our R direction, right? Because we're integrating over the whole radius of the disk. And then in the phi direction, we're going to be integrating from 0 to 2 pi. And then here we have sigma over R squared plus Z squared. It's squared on the bottom. And then we have cosine theta R dr d phi in the z hat direction. And our cosine theta is going to be exactly the same as our previous two, where it's just going to be, we could look at this angle here, theta, and say, okay, it's adjacent over hypotenuse. We just want that vertical side. So we want z over z squared plus r squared. And that is our cosine. Okay, so now let's rewrite this. So we have 1 over 4 pi epsilon naught. We have our 2D integral. We have a 3/2 down here, and then we have r dr d phi. Now we can see right away that there's nothing that depends on phi in our integral. So the d phi part, we can get rid of that because we're only going to basically be integrating from 0 to 2 pi over d phi, which will just give us 2 pi again. So we can just sort of immediately do that integral and make it a 2 pi. So now we're just left with r dr. So let me just put this over here. Okay, and then I'm also going to pull out my sigma and my z, since those are also constants in this case. So I'm just going to rewrite my sigma and my z out here, and then I just have r and dr here. And this whole integral is in the z hat direction. Okay, and this was from our d phi piece. Okay, so now this integral. So this integral you can do by hand. You'd have to do a u substitution. I would expect my students to do a u substitution if you're at the level of Griffiths and you're doing double and triple integrals, you're doing polar and cylindrical coordinates. A basic u substitution like this is definitely something you should know how to do. So I would expect my students to be able to do this by hand. So if you want me to do a separate video about how to do both the previous integral that we just looked up and this integral, I can do that. Just let me know. So this one I'm also just going to write down the answer, since I'm most concerned with that you understand how to set up these integrals and basically get to this step. Then integrating is like a separate skill. So, okay, so I'm just going to write down the answer to this. But if you wanted to do a u substitution, you would do u is equal to r squared plus z squared, and then your du is 2r dr, blah, blah, blah. Okay, so let me know if you want me to go through the details of that in a different video. All right, so this integral will come out to -1 r squared plus z squared square root, and then from 0 to capital R. All right, so now we plug in the r and the 0, we'll end up with -1 over r squared plus z squared square root, and then minus a negative, so we have plus 1 over 0 plus z squared square root would just give us z. Okay, so now we can write our final answer. So we have the electric field is equal to 1 over 4 pi. Again, I'm just going to leave my 1 over 4 pi alone. And then I have 2 pi sigma z. And then I'm just going to put my positive term first, so it's a little neater. And then this is all in the z hat direction. Okay, so that's my final answer now. So this final answer is probably our ugliest one. And then it asks about what happens when r goes to infinity and when z goes to infinity. So I'm not going to go through the details of that here, but if you took the radius of this disk to infinity, that would look like an infinite plane or an infinite surface charge. So you would expect this, when you take r to infinity, to look like that of an infinite surface charge. If you take z to infinity, that means that you look infinitely far away. You would expect this to look like a point charge, because if you have a really tiny little disk and you're super far away, you would expect that to just look like a point charge. So you have to use some tricks to make this look like the electric field of a point charge in the limit z goes to infinity, but it can be done. And then the same thing will happen for our previous ones. If you take z goes to infinity here and here, you'll get the electric field of a point charge. Because all three of these cases, when you're very, very far away, will look like a point charge. Okay, so that's it for today. Next time we'll do these exact same scenarios, but we're going to use the potential to find the electric field instead, and you'll see it's much, much easier to do it that way. All right, so I'll see you guys next time.